Hi everyone, thanks for being here today. I'm excited to tell you about how we're using Julia, SciML, and Puma's QSP for QSP modeling at Sanofi. First off, just a quick outline of my talk. I'll talk about the background of QSP modeling at Sanofi before getting into our goals of how we want to use Julia Hub. I'll next introduce our model for the case study before getting into modeling and simulation activities, and then I'll end with our future work. So we've already had another speaker talk about QSP, but a little more background on it. It's a mechanism-focused, multi-scale systems biology modeling approach that's based on disease biology and drug pharmacology. The strength of the approach is that it incorporates a lot of prior knowledge from multiple scales, from in vitro to clinical level data, as shown in the figure. And then this allows for new predictions to be made. And so you can look into things like combination therapies, diverse patient cohorts, and make predictions about outcomes over time. It's growing a lot more common in oncology and immuno-oncology spaces, and especially with the FDA's Project Optimus, which is trying to have push for multiple support before moving on to certain doses in clinical trials. Doing this in silico is very helpful. At Sanofi, we have a team of around 20 scientists, and we're working in 3 different disease areas. Historically, our group has used MATLAB, and our group and also QSP at large has often used MATLAB and then SymBiology for QSP modeling because of the ODE solver capabilities. But in our current workflow, we're running into issues. Some of our models can have like tens of ODEs, but we do have some very large scale models where we're measuring over 1,000 states over time. And so we found that the internal MATLAB solvers like ODE15S just aren't compiling in a fast enough time. To combat this, we've been using wrapper codes that help us access C-based solvers like sundials via the creation of MEX files, but it's not super pleasant to work with MEX files, and debugging isn't the best. So really, we've been interested in speeding up our sort of workflow in 2 different areas. We would love to have tools that have faster solve times than what we're currently doing, because we're doing a lot of optimization-heavy processes. And also, if we had tools that helped us speed up the time that it takes for us to write and perform our downstream analyses, that would also be helpful. We do global sensitivity analyses, and we create virtual populations for almost all of our models, but for each new model, we're kind of writing a new script in these cases. And so we've been really interested in what Julia and tools like SciML and Puma's QSP have to offer. With SciML, the large number of faster differential equation solvers all written in the same language, and with Puma's QSP starting to incorporate more one-liner functions for like GSA and VPOP. And we love how much everything really works together, works well together, all of these packages in their communication, and also interested in the cloud computing capability. So that brings us to the case study. I'm going to talk today about an in vitro QSP model that we've made based on a multi-specific immune cell engager molecule that's in development at Sanofi. This molecule brings together immune cells and target cells and makes a physical synapse, a connection between the two. This helps increase cell killing. And so we're modeling both cell level processes like killing and cell activation, as well as receptor level, the binding and shedding. This model in the future will be used to answer questions about dose amount, scheduling, efficacy, safety, and also combination therapies. This is our model diagram. And so again, it's really centered around the synapses that can form between immune cells and target cells. In addition to synapses between immune cells and target cells, there are also some healthy cells that express the receptor that's also found on the engager, and you have synapses there as well. For our immune cells in particular, synapses allow for either changes in state from immature to 2 types of activated cells, and also we include exhaustion in the model as well. And then as you can see, we have like killing and cytokine secretion. Overall in this model, we're modeling 356 ODEs, or state variables. So generally, in the end, our QSP models are informed by multiple types of data, from in vitro to clinical. Today, we're just looking at in vitro data. We have a lot of in vitro data in this area, but today we're just going to be doing some exercises with the cytotoxicity and activation data that we have. And the way that that data looks like for in vitro, it's a little different than in clinical trials. In vitro, you have multiple wells that have the same starting conditions, but each well receives a different dose. So the data, and then all the wells are cultured for the same amount of time, and then a measurement is taken at the same time point. So then the data, in the end, you're plotting over dose as opposed to over time. And so, so now, kind of with the background and then where we started biologically, I'm going to get more into how we coded things. I'll talk about how we generated the model and what sort of tools we used, and then show some calibration and virtual patient generation information. So in this case, we had actually written our model in MATLAB beforehand, so we just used text editors like regex to help us change the syntax from a MATLAB to a Julia-friendly syntax. And that ends up looking something like this. First, we define all of our parameters and variables and their initial conditions at the start of the script, and then we have a large block that lists out all of our ODEs. We also define algebraic terms that help us define how exactly are we defining things like activation and cytotoxicity in our model, so then we can later pull that in for our cost function evaluation. After all of those things are defined, then we can create the ODE system. We also use structural simplify because we've included some algebraic terms, and then we're able to define our ODE function. And so after we defined our function in Julia, we just wanted to make sure that since we had the model in MATLAB already, that there was alignment across the two. And so we performed a simulation with 3 immune cell types, the target, and then 1 dose of drug, and we simulated over 200 hours. And on the screen, I've plotted the cell counts and also the MATLAB and the Julia results at the same time. There's really great alignment. It's a little hard to even see the MATLAB results, but they're just laid over. And what we were really excited about was that we're able to run MATLAB in the cloud in a similar environment to Julia Hub, and we saw that Julia Hub was 37 times faster than our sped up MATLAB simulation. So this was not using an internal MATLAB solver. This was already like fast MATLAB. So we love to see that speed up. After we had our model, then we started to move it more into Puma's QSP, and Puma's QSP is really based around the idea of the trial. And so for our in vitro case, we defined trials for each of the doses that was explored in our 2 experiments. And so this is the syntax of our trial. We give it the data that we want to match in our calibration at that dose. We define initial conditions, the cost function, and the dose as well. After defining our trials, we also then defined our parameters for calibration. We ended up, in this example, we were calibrating 11 parameters, and these were chosen based on how they were related to the cell functions that were explored in the activation and cytotoxicity experiments. Lastly, we defined our inverse problem based on the experimental data and the model, and then the parameter search space, and we were able to calibrate. And this was our calibration result across the 2 experiments. We were pleased with these results. It's often hard to calibrate across 2 experiments at the same time, and so we love to see the close fit to the activation data. And for the cytotoxicity data, we're getting pretty close on the lower end, and in this sigmoidal middle part of the curve, we're also close to the data as well. So this was great, and then we started to explore virtual patient generation. So this is an in vitro system. It's not necessarily a real patient, but excited to look into this and get more used to it for when we do move on to clinical trials. And so we generated a population of 200 patients. I have the average population plotted in blue, and then 10 simulations of 10 patients in the lines. And so we loved to see that, especially in the cytotoxicity data, we are getting diversity in the response. We're getting some simulations above the data and some below the data, which is something that we look for then in clinical trials. You need to make sure you do hit those extremes at that point. So that brings, future work, we are going to keep working in the system, working on calibration with all in vitro data sets, and then we'll expand this model to our clinical model, which will involve doubling the number of ODEs because we'll be adding more compartments. We're also excited to keep working on learning more of the options and what works best for the virtual population algorithm in Puma's QSP, and also looking into prevalence weighting in different projects where we already have clinical data. And lastly, we'll be exploring possibly looking into an identifiability analyses. That's not something we really do right now, and also GSA. I couldn't have done this work alone. I'd love to thank my colleagues at Sanofi, Kamau and Christine, and at Julia. Thank you to Arno for helping us get this model running. Thanks to Matt, and also to the organizers of this session. And thank you all for listening. Happy to take any questions.
Thank you very much. I took over the baton from Paul for the chairing of this session. I'm not at Julia Hub, and we kind of ended up on the organizing committee by accident.
I was like, oh, your name's on the list.
At least I can do is chair.
So did you try to make a video streaming? So thank you. It was really interesting to see the speed up of the simulation time, but did you try to quantify the source of it? So did you try to run Julia with the sundial CVOD solver to see if it was maybe a modeling toolkit that did the magic?
Oh, no, we didn't try that. We were using, a different solver within Julia. But yeah, that's something, you're right, that's an even better comparison to do, yeah.
Is there anything that you missed from MATLAB when you switched to Julia? Something that MATLAB had that you would wish you had now?
That's a good question. Yeah, I think something we had already talked about, we had been interested in, we were using prevalence weighting in a different model that we had been working on, and so we did talk with the development team, and they implemented prevalence weighting in Julia Hub. We haven't had a chance yet to do that comparison, but that's something to compare MATLAB to Julia with the exact prevalence weighting algorithm we were using. So right now I can't think of anything else.
Thank you for the talk. I was wondering, you mentioned identifiability analysis. So your system of equations is 350 something, and probably your parameters is at least 3 times that. So what do you hope to see out of an identifiability analysis? Because I think you probably know the answer already.
Yeah, I think this is something that our group has always talked about, looking into, and just we haven't really looked into it, and it might just be a little easier to start doing that with Julia. But yeah, yes, some sort of future plan, yeah.
Great talk. I have more of a biological question. I'm just curious about, so the activation models you use seem to have, just immune cells and tumor cells. So I was wondering, when you think about kind of like in a clinical context, you'll have other cells in the tumor microenvironment, right, that are immunosuppressive, other physical characteristics of a patient tumor. So I was wondering, taking that into context, how well did these models actually translate into the clinical realm? Or are there adjustments that you need to make at that level to make them more viable? Yeah,
that's a great question. And normally those in vitro data that you start with are really targeted. So they help us figure out things like the activation rate and the killing rate. And so then we start there and we're able to use those parameters from in vitro. And then when we scale up to the clinical model, we do include other cell types, other sort of processes, but it's nice that some things are already known from in vitro, so then we're still calibrating at the clinical level to clinical data, but we just have to calibrate less parameters at one time then.
Okay, if you don't have any more questions, that's the
Thank
next
you.
speaker. Thank you.